I'm going to talk about, as Ernesto said, thanks for the introduction, about my new book, Autographic Design, which came out last December. And it's very much based on my experiences teaching data visualization. It is also an invitation to expand our idea about data and our idea about data visualization. So in a way, also a critique of the discipline. And it was very much shaped also by my experiences teaching, generations of students in different places. And I just want to, this is the book, want to jump back in time to a project when I was still at a different institution in Austria at the Art University in Linz from 2007. A project by 3 students called Garden of Eden, where they visualized air pollution by creating this kind of box and filling it with toxic gas in the equivalent of the air pollution of different cities around the world, and having a poor salad plant in there. And by the condition of the salad plant, you could kind of guess about the air quality level. So this kind of idea was very early. It was a very strong statement. Also a kind of giving off agency about the visualization, where now you have something that is not fully under your control to express data. Then data physicalization, which is now a kind of a very popular topic for 10 years now. Students always, come to try to express data in physical form. Those are 2 projects from our IDDV program in Boston. First is about showing the impact of the flood in Houston in relation to the socioeconomic status of the different parts of the city, expressed in the vertical displacement of the map. And another one by Aaron Tang was a kind of a contagion model visualization, where he also created a physicalization of it in this 3D. So those are examples of projects that started as data visualizations, but then expanded this idea, mapped it to physical form, which is what data physicalization is about. So there is this definition by the framers, Ivan Jansen and Pierre Dragicevic, is that traditional visualizations map data to pixels or ink, whereas physical visualizations map data to physical form. So this is based on a very simple conceptual model of data visualization that I think many of you know, where you have basically, if you want to choose which mark or which visual language you want to use for a visualization, you start with the data type and with the task that you want to accomplish. This is very simplified, but it is a very fundamental idea in data visualization that is basically repeated in many different ways. And it's actually coming from cartography, but it's also extended or expanded to data physicalization. So there's a problem with this model, which is that it's framed from the perspective of the designer. As a designer, you know what you need to do in order to create an artifact. But from the perspective of the recipient, it's much more difficult. So you can't simply reverse that model. You have to first know a few things in order to even recognize what the visual language is, and then basically reverse engineer it to find your way back to what kind of data you are interpreting. And if you expand this model to physical space, then you're complicating issues tremendously. And I think this is a good thing, but it makes this conceptual model a little bit problematic. So this is a data physicalization, also a kind of an artistic project by designer Adrian Siegel, who, when you see this object, it looks kind of, intriguing in its complexity. You have to know that it is a map of a river that, something is wrong with this mic, I don't know, that is changing throughout the years. And so the dimension, the depth dimension is basically the time axis, and you see how the river changes throughout time. So easy enough, but if you don't really know that, you have a hard time figuring that out. But then there are also very interesting details. So if you look at all of these little lines here that may come from a laser cutter, the tool traces of the fabrication mode, they are actually very important because they evoke a comparison to, let's say, tree rings or something like these kind of geological formations that emerge over time. So there's this close connection to time, but they don't really. This doesn't really fit into this conceptual model of data visualization. It doesn't really rise to the status of a visual variable. So, and I think that's a good thing, because there are certain aspects and certain small clues that the materiality of the object provides that are picked up in the way how we interpret the object, but that really don't play a role in this underlying conceptual model. And I want to show another example that illustrates this problem, or this interesting issue, which is a project by a former master student, now a PhD student in the information design program in Boston, Sky Moret, together with Lina Klaus and Moritz Stefana. So this is a project where they collected plastic trash on a beach in Bali and created a kind of a physicalization, a diagram that illustrates how much plastic is discarded, recycled, incinerated, still in use. And if you look closer, it's basically consists of those different diverse pieces of plastic trash. So according to our conceptual model, it's very simple, because it's basically a very simple diagram. It's basically just a relationship between 4 different quantities. But if you think about the clues and the traces that are embedded, it actually contains much more information. So we could, for example, look at these plastic pieces as also a form of data. So they have, just like a data set, they have been collected, they have been sorted, they have been categorized. You can rearrange them, you can use them for different things, you can study all kinds of things, whether certain qualities are with certain objects fall apart quicker than others, and so on. So in a way, it is like physical data, and that's basically one of my main premises, that we can think of physical objects as data, not just as proxies of data, but as actual manifestations of data. And I think those qualities also are really important for these projects. And I also noticed that in the area of cities, grassroots science, environmental activism, advocacy, I noticed a couple of years ago a trend to move back to very analog ways of representing environmental issues. So if you remember, 10 years ago, there was this huge push of data literacy for environmental activists. So there's the Practical Tech Collective, School of Data initiative, and things like that, where say, okay, you have to learn how to work with data. and use data visualizations and so on. But now we see a lot of very analog ways that seem to make a resurgence. This is an example of New Jersey, where a local group who is looking at air pollution is kind of documenting instances like that, where a local incinerator has this pink smoke, which, according to them, is an indication that this incinerator is incinerating medical waste, which it's not permitted to do, and which has problematic issues for the local community. And yeah, I mean, it's a of course they also measure the air quality, but those kind of representations of the phenomenon itself, not so much the data representation of it. This is a very powerful thing. And there are many similar examples. This is another example that I discuss in the book. This is started in New York with bicycle activists who were advocating for larger space for pedestrians and cyclists. And they do so by documenting the traces in the snow of the snowstorm, and then overlay, ideas what could be done with those extra spaces that are not touched by cars, arguing that, well, this is the evidence that cars don't really need that space. If everyone drives a little bit slower, then we could expand the space of pedestrians. So there are many different reasons why such strategies and tactics of evidence presentation have advantages over traditional data visualizations, which I will discuss a little bit later. But I want to first talk a little bit about what I mean by autography. So autography related to traces means self-writing and self-inscription. So pretty much everything that happens leaves a trace, every contact leaves a trace. And this is pretty well captured in this short section by Ralph Waldo Emerson, who writes, "Nature will be reported. All things are engaged in writing the history. The planet, the pebble, goes attended by its shadow. The rolling rock leaves its scratches on the mountain." So he goes on to just discuss or mention a lot of different ways how nature inscribes itself, until he arrives at the point where he says also the memories that we have are actually physical inscriptions in our body, which I would say is also consistent with how we know how memories work. But it also shows that this rises now to the level of an epistemic paradigm. Yeah, so the trace in the late 19th century was a very central epistemic paradigm that maybe it's related to the emergence of photography, maybe it's related to the medical semiotics. But this idea that a trace is a conduit for knowledge production was very central. And in some way, this is still relevant. I mean, if we think about the kind of data sources that climate scientists use, ice cores, tree rings, sediment data, coral layers, they're often called proxy data sources. In meteorology, there's also the term of autographic data, that is trace data. And sometimes those are also living beings like plants or animals, sentinel species that warn us about things that are happening, the proverbial canary in the coal mine. And also, water quality of oceans is monitored by mussel watch programs, which are more reliable and accurate than many electronic measurement methods, or lichen for air quality monitoring is another example. So you see there are many different examples of that. So let me now think a little bit about how, what is the advantage of using this, and what is the relevance? Maybe back to the bicycle activists. So the normal approach would be, okay, let's use GIS and let's use traffic simulations in order to make an argument for the expansion of, of public space for pedestrians. But there's one disadvantage if you're doing that. I mean, of course, everyone is, they're still doing that, but there's one disadvantage. If you basically adopt the representational methods of a particular, expert or a kind of institutional approach, then you are always, on slight disadvantage. You are always opening yourself up to criticism that, the way how you simulated that, or your data is not accurate enough and you're not using scientific methods. So you're always at a kind of argument, at a disadvantage. However, if you show the phenomenon itself and if you basically, show the traces, then you are in a way challenging the experts to explain. You pull them onto your side and ask them to explain the phenomenon that you are showing. So there's a certain institutional politics around modes of representation and the use of data collection methods. And I think this is especially important because if we look at today's big controversies, they are, from climate change to pollution to fake news, disinformation, they mostly revolve around questions of how data were generated and less about how existing data that is taken at face value should be interpreted. So data visualization is at a slight disadvantage because it doesn't really show very much about how data were collected. I mean, it contains also some clues about that, but the effect that once a data set exists, that we more or less forget how the data were collected is a very big issue. So this is where I see how data visualization works in that space. You start with the data, you move in this symbolic space of recombining, analyzing data in order to interpret the phenomenon, but that phenomenon is outside. You don't have direct access to it. Autographic design now has a different approach. You start with the phenomenon and you look at the way how data are generated in order to contextualize analysis. So the goal is a very different one. It's really about the data generation process and less about the interpretation of data. Or you could say that data visualization begins with data and autographic design ends with data. And I created a model that combines these different design operations of autographic design, kind of divided it into 4 steps. This is a very preliminary model, but it captures a wide range of different design strategies at this space between the phenomenon and data. And I just want to very briefly go through it. So the first thing under focus is the strategy of framing. And this is the most elementary autographic design operation where you're just framing a phenomenon. Like what we see here is a 18th century instrument for measuring the blueness of the sky. And that was here reenacted by 2 Swiss artists. So basically, it's just creating a frame around the phenomenon and telling you, look here. Constraining is a little bit more intensive. It involves constraining the phenomenon. So in order to observe the expansion of liquid in a thermometer, you have to constrain the liquid into this glass tube, and then you can observe its expansion. Otherwise, you won't be able to do that. The next step would be is what I call tuning. So you usually many traces are not intense enough. You don't really see them. So you need to first aggregate them until you are able to observe a change. This is how you measure particulate matter, air pollution. You basically just have a clean filter, and then at some point it looks like that. You put it on a very fine scale and measure the weight difference. This is one way of measuring particulate matter. Often you need to do the opposite. You need to separate something. This is paper chromatography that is used by organic farmers, where they kind of analyze soil composition by putting the soil in, in a piece of paper cone, and then the water particles are, pulling it apart. And so then you can kind of see which components are in your soil sample. The next step is about situations where you have basically an imperceptible phenomenon. For example, we cannot really see the wind. We only see things that are moved by the wind. So coupling means introducing something that interacts with the phenomenon that you can observe, like a tracer substance that helps you observe water currents or things like that. And registering means creating permanent traces of something. This is where all the autographic meteorological instruments come from. This is a newer version of one of the earliest instruments, the sunshine recorder from the, started in the 18th century. It's basically a lens that bundles the sunlight and burns a trace into a paper strip. And this helps you measure how many hours of sunlight you have during the day. Like when there are clouds, then it's interrupted, so you have almost like a barcode. And now when we go to the data side, the very last point. This is where human-made traces come into the picture. Traces are usually trace narratives. You have to annotate what you see in your process of interpreting traces. So annotation, highlighting, as in this case of traffic accident forensics. And then here is where we close the loop. Here we are now back in our traditional idea of data, where we are mapping some aspect of the phenomenon to a quantitative value using a scale. So while I developed this system, I also used or created different art projects that helped me examine help me theorize it. I don't know if we have a lot of time for it, but those are two projects. The first one, dust mark, dealing with particulate matter pollution in a German city that has a lot of it and has a lot of public controversies around that. And you have the situation where the city, basically puts up air monitoring stations, but the citizens contest it and say, well, they are in the wrong places and they don't really measure what is relevant. So again, you have a controversy that is around the data collection method and not about the visualization of the air quality data. So, but what these citizen groups did is they created a sensor network, which is now a very successful global project, where they, collected best practices to, deploy low-cost optical dust sensors, and those sensors give you a number. So now you have the problem: how do you contextualize that number? How do you make sense of what that actually means? And so my approach here was to use the city as a visualization of air pollution, because dust accumulates everywhere. And you only are able to estimate it once you start cleaning it. So this is exactly what we did. Yeah, that's a technique called reverse graffiti, where you use a pressure washer to clean out particular areas. This pattern is designed in a way so you can watch the dust reaccumulate after application. So these very fine parts are the first one that disappears. You kind of can estimate as it accumulates back. And this is, not meant as a alternative measurement, but as a context. So you're invited to, think about to think about whether, areas that have a very high reading, do they also show you, very high dust pollution in these dust marks. And then it also invites criticism, because you say, well, actually, it's not just dust. There are also other things. There are algae. There are other objects. And of course, this is totally right. I mean, but at the same time, what happens is when you recognize the shortcomings of these methods is that you are engaging with the materiality of the process, which is something that you cannot do with the black box of the sensor. So the sensor also has simplifications, it also has shortcomings, but you only get the number. You don't really get to observe those, which is the idea here. This is another project later dealing with another air pollutant, ozone, and this is based on plant indicators that ozone, ground level ozone is a very corrosive gas that is very difficult to measure. It's less frequently measured compared to particulate matter, and it damages plants, and it also has negative effects on the respiratory system. So what farmers discovered early on in the 20th century is that ground level ozone ruined their tobacco plants. So tobacco is a very good indicator that was later closely examined by the US government. So they created a visualization system where they used different phenotypes of the tobacco plant at different sensitivity levels towards ozone to basically allow this kind of visualization through the plant itself. And they, observe them. The idea here was similar to the dust mark, where it create a tattoo on the plant itself, like a legend on a map, which turned out to be very complicated. So I built a machine to do that. But ozone is a very volatile gas. But I created this ozone garden, which is also a community practice that is used in different places in the US to create these kind of gardens that allow communities to observe indicator plants. Also a recent project that we got published at CAI, where we use an autographic method to register touch interactions on surfaces. This was another outcome of the pandemic, where suddenly everyone was really concerned about touching surfaces. And through that concern, we suddenly really got very much aware of how much we depend on touching things without noticing it. So we started studying this by applying a kind of an invisible tracer substance onto objects, onto data visualizations. And we are measuring how people touch the object as they are trying to interpret the data. And then you can kind of visualize that under UV light, and then kind of create this kind of aggregate image of the touch trace, which is a very cheap solution, because registering touch on arbitrary surfaces is a kind of still a hard technical problem. But I don't want to stop with just observing phenomena. I think the autographic design also has a computational dimension. It allows us to compute with materials. And when we talk about analog technology, we are talking about an analog situation between two different phenomena. Usually there's one phenomenon that we have under control and one phenomenon that we don't have under control, but they are somehow analog to each other, so we can kind of use one of them to study the other. And one example is the wind tunnel, which was called an analog computer for calculating turbulence, which was until the 60s very difficult to compute because it requires a lot of computational power. But with a wind tunnel, you get the result instantaneously. So you just have to measure it, which is another problem that analog computers have. But it is interesting in multiple ways. I mean, first of all, you couldn't have airplanes without a wind tunnel, so you really rely on these calculations. But you can only build a wind tunnel if you also understand the math of fluid dynamics. So the traces that the wind tunnel generates is a good example of traces that are not just things that we naively find in the environment, but things that are based on ideas, based on theories, based on assumptions, and based on ideologies. So all of these things are baked into the traces because they're baked into the apparatus that is used to generate these traces. This is a wind tunnel in Zurich that is run by a group of artists that is basically built out of waste material. And so they have a wind tunnel journal and a wind tunnel festival where they do all kinds of experiments with the wind tunnel. Another example, since material computation, I mean, there's so many different possibilities to come up with these analogies for computational purposes that it has a very interesting speculative and imaginary perspective. So this is a project by artist Ebru Kurbak, who is very interested in alternative technological futures, specifically based or connected to skills that are often closely associated with female labor, such as textiles and textile craft. And so she came up with this idea, like, what if the tape recorder would use yarn instead of, magnetic tape? So she built a tape recorder using magnetic yarn to record audio that actually works, and basically shows this kind of way how it could have been different. But the really fun thing was that as soon as they have developed with her collaborator, as soon as they built this device, they found out that actually the original patent from the, I think, late 19th century to build a magnetic tape recorder was using yarn. Just the inventor back then was not really able to implement it reliably, but it was actually the beginning of that invention. So we see that there are a lot of really interesting cultural, gendered, and other aspects into the way how we look at cultures of computation. And to close that story, to come back to digital data, I want to talk about the autographic aspects of digital data a little bit. And this is also an area where I'm still currently working on. Just published a paper in Big Data and Society about synthetic data as a non-representational mode of data. But the question is, what would be a genuine digital trace or physical trace in digital space? And like one thing that immediately might come to mind is the glitch, where you have, let's say, a physical disruption of a digital system that causes, an image to be corrupted. And when you look at the image, sometimes you can still see it. And Rosa Menkman did an amazing art project a long time ago where she investigated different file formats, how they respond to corruption. And by looking at these artifacts and these traces as visualizations, you learn a lot about how the algorithm of encoding the visual information works. So it is in a way a very direct equivalent of a trace. But I also think that in a way we could look at every kind of data as an autographic trace. So if you think about going back to the air quality measurement, if you now basically, look at the, the line on a drum roll of a chart recorder as a physical trace of a seismograph, or you exchange this with a digital sensor and a hard drive, that is exactly the same thing. It's just there are a couple of additional steps of translations. So the digital data that you have at the end is also a physical trace. But I think the interesting thing here is that there are still a couple of aspects of the apparatus of data collection that inscribes itself into the digital data. So this is, for example, a data set that is often used in big data competitions. It's kind of the drop-off and pick-up locations of all taxi trips in New York, and you can go to the website and download it for every single year. And when you start plotting just the geographical coordinates on a map, you will get an image of Manhattan. Not very surprising. But one interesting thing is now it's more blurry in some areas than others. Can anyone guess what this kind of blurriness results from?
The answer, but I won't spoil it.
Yeah, it's exactly. So why GPS noise? Tall buildings, yeah, that's exactly right. So you see, like in Midtown, you have a lot of tall buildings, you have a lot of noise. So, but think about what that means is that the two-dimensional data points contain information about the three-dimensional shape of the city. But you can only access this information if you take the materiality of the data generation process into account. You have to understand that this comes from GPS and not by, let's say, geocoding street addresses, which would kind of introduce different error patterns. And that is a kind of an autographic aspect that inscribes itself into the data. So from that perspective, all data have a kind of an autographic aspect, but it's kind of a non-representational. It's not intended to show anything. It's incidental. So if you think about the autograph, your signature, the relevant information is not necessarily how you spell your name, because there are different ways to find that out. But all those involuntary movements as you are writing your name, that even you yourself don't have fully under control, and that therefore has this kind of incidental evidentiary value. So this is in a way what was really interesting for me. And of course, I mean, there's much more to say. There's also an issue, there's a danger of not, falling into a naive positivism around traces. And I think it's important to think about it that, the traces are not necessarily information about reality. They are information as reality. So they have their own reality. And in the book, I have this joke where I say, from the autographic design perspective, every data are objective. Everything is objective because the data are object-like. And that does not mean that it refers to an external truth, but only refers to itself as its own as its own reality, which of course, doesn't really tell us those things that we expect data to tell us, but it also shows or presents things that are otherwise often overlooked. And yeah, I'm gonna stop here. Thank you.